Alright, so in this video we're going to do an example of a calorimetry calculation. But first, let's do some review of completing and balancing chemical reactions. So we're first asked to write the chemical equation for the reaction between aqueous sulfuric acid and aqueous potassium hydroxide. So sulfuric acid, right? The IC ending means that it came from the 8 polyatomic ion. So it must have come from sulfate. Right, so we've got sulfate is SO4 2 minus, so sulfuric acid is H2SO4, and then we're reacting that with potassium hydroxide. So potassium is an alkali metal, it's K+, hydroxide is OH minus, so I have KOH. Right, and so the ions I have present here is I have H plus and SO4 2 minus from the sulfuric acid. I have K plus and OH minus from the potassium hydroxide. And so I'm going to combine the sulfate and the potassium and the hydroxide and the H plus ions. So this is an acid-base reaction. So the H plus and OH minus is going to give me water. And then I need 2 potassiums for every sulfate, so I'm going to have K2SO4. And then to balance this, right, that's a liquid. All common salts of alkali metals are soluble based on our solubility rules, so K2SO4 is going to be aqueous. And to balance this, I need 2 potassium hydroxides and 2 waters. So that would be our balanced chemical reaction. So let's go on to the calorimetry part of the example. Alright, so we've got the same reaction on top that we've already completed and balanced. And we're told we have 25 milliliters of 0.5 molar sulfuric acid and 25 milliliters of 1 molar potassium hydroxide. The temperature starts out at 23.50. It rises to 30.17 when these reagents are mixed. And we want to calculate the heat of the reaction, the Q for the reaction. And we're going to assume the total volume is the sum of the volumes of the solutions, and it has a density of 1 gram per milliliter, and the specific heat is 4.184 joules per gram degree Celsius. So we're going to use the fact whenever we do this calorimetry, right, the solution is the surroundings and the system is the reaction. And they're going to have, the surroundings of the system are going to have equal magnitude but opposite signs. So the Q for the solution is the negative Q of the reaction. And for the Q for the solution, I can calculate that directly using the MC delta T formula, because we're told we can assume that the total volume is the sum of the volumes of the solutions. So I have 25 milliliters and 25 milliliters. So for my solution, I'm going to have 50 milliliters. But we're told to assume that the density is the same as that of water. So if the solution has a density of 1 gram per milliliter, then if I have 50 milliliters, then the mass of the solution is 50 grams. We're told to use the specific heat of water for the heat capacity, the specific heat capacity of the solution. So I know C delta T right, always final minus initial. I get 6.67 for the delta T. So I can plug in what I have. I have 50 grams. I have the specific heat of the solution. My delta T is 6.67 degrees Celsius. So the Celsius cancels, the grams cancel. I'll be left with joules. The Q for the solution that I get is, my calculator spits out 1395 0.4 joules. And then if I go to the correct sig figs, I have 3 sig figs, 4 sig figs, 3 sig figs. So to 3 significant figures, I can't write 1395.4, right? Because I want to keep the 1, the 3, and the 9. The 5 is going to round the 9 up to the 39 up to a 40, and so I can't just write that because that would only be 2 significant figures. So I need to write it in scientific notation. So the Q of the solution is that many joules, and the Q for the reaction is going to have the opposite sign. So the Q reaction is minus 1.40 times 10 to the 2 joules.